Thank you for taking the time to join us today and for your interest in our continuing education course, Efficient Design Utilizing Decorative Guardrails. As a leader in decorative metal railings, it is our intention to help you with the basics regarding the importance of our products in your design process, ensuring safety while maintaining design intent and aesthetics required for successful end results. Working together from concept to completion with the brightest and most experienced teams in a collaborative effort is the key to any project success. With all this in mind, let's begin our journey together, starting with defining the purpose and learning objectives of this course. The purpose is ultimately to help you examine guardrails in terms of their structure, safety, and style while addressing specific IBC codes, materials, finishes, and infill options. All these items are critical to your design, and many of your choices will affect project budgets. As we work our way through this material, we hope that the end result will give you a foundation to begin the design process incorporating guardrails into your projects. At the end of the presentation, you will be able to explain how loading requirements, member selection, and deflection affect guardrail systems design and performance. Recall 2018 IBC code criteria related to handrails and guards, and apply the criteria to the design of a safe guardrail system. Discuss the advantages and considerations of three types of glass guardrail support systems. Specify guardrail materials, finishes, and infills that are appropriate for the project environment, design goal, aesthetics, and budget. When you think about guardrails and how they function in a building, there are basic considerations, or what we like to call the three S's of railing design: structure, safety, and style. Our examination of these three key factors will give you the tools and understanding on how the structure and safety impact the final style and design. Let's begin with the structure. For railing to achieve performance requirements, the focus must be on the method by which the railing is affixed to the structure. Attention should also be paid to the sizes and shapes used in the railing construction of the railing. Next is safety and the structural considerations that are driven by a variety of performance requirements that are outlined within building codes. Style is obvious and will be determined by each designer's vision for the project. So let's talk first about some of the loading requirements for railing. If I haven't introduced myself already, I'm Tony Barnes. I'm the structural engineer here at Sightline Commercial. And I think that in my experience, in most jobs, the technical details are left to us engineers, but I think that the most successful projects I've been a part of are when all the team members have some understanding of the technical requirements, and those discussions about those requirements and how they relate to the structure and the aesthetic are had early and often in the project lifecycle. And generally, so let's talk about the general meaning of what a loading requirement is. That's simply the forces that are required to be applied to a railing that that railing must resist. They come from things like gravity or dead loads, human activity, live loads, which are the most important for railing, and the environment: seismic, wind, snow, temperature. Live loads or wind loads on exterior structures almost always determine the construction of railing. Seismic loads can occasionally affect design in high seismic regions such as California. Temperature loads are caused by expansion or contraction of the railing due to changes in temperature. Note the live loading requirement is either 200 pounds concentrated, or a load applied to a discrete area, or 50 pounds per foot. So that's a linear load that's applied across the entire length of a railing. It's usually applied laterally at the top of the railing to create the highest stresses in the railing, which is what the code requires. And these live loads almost always control for interior applications. This load requirement has essentially been unchanged for 30 years and is used as a way to design a system for an abrupt load a guard might see if a person falls into it or multiple people lean on it. Wind loads occur on an exterior railing and that load varies based on geographical location. The eastern seaboard down through the Gulf see much higher wind loads when compared to most interior regions. There's some mountain regions that are exceptions. They have special wind zones that you have to look at per the exact location. The wind loads are a function of wind speeds. Gust speeds are currently provided in AIA 716, and wind loads are calculated based on these wind speeds, as well as other factors including but not limited to the surrounding topography, location of the building relative to other buildings, and any abrupt changes in topography. In addition, the wind load is dependent on the position of the railing on a building. Railings on taller buildings and railings that also might act as parapets on the top of roofs will see higher wind loads. In subcoastal locations, such as some jurisdictions in Florida, windborne debris testing is also required to make certain guardrails will remain in place after they are impacted by debris during hurricanes. Oftentimes this is called missile testing. Because the location of a building amongst other buildings greatly affects wind loads, many taller buildings in urban areas utilize wind tunnel studies. This has become much more prevalent in the past 10 years or so because the technology has gotten and computers have gotten faster. That uses a small urban scale or urban model that's scaled down with pressure measurement devices attached to those buildings that determines pressures on specific areas or pieces of the building. This is allowed by code in lieu of calculated wind loads, except in New York City, where the greater of the wind tunnel study and a calculation must be used. So in conclusion, loads are very important in the design of railings. It's really where everything starts. They should be considered as early as possible in design, and a competent professional engineer should be engaged to make certain the building structure can adequately support the railing. Interior railings, supporting primarily the live load, as we discussed, can usually be supported readily by most construction types. However, sometimes you're on a thin stair or a non-structural finish such as stone or terrazzo. You sometimes need to change that or think about that. That might prevent the adequate railing attachment. These issues are usually mitigated by early design coordination. For exterior railings, which might see much higher wind loads, you may require a special structural accommodation going down through the slab, for example, down to the steel or into a concrete beam. As stated previously, scheduling delays and costly changes can be avoided by simply addressing those loading requirements early in the design. Let's talk a little bit about safety factors. Understanding the loading is a nice segue into this topic. We'll discuss our next S in the slide previously presented. That is safety, and safety factors are an important concept to understand. Safely engineering structures means that the stress or load induced in structural elements be below the structural capacity of the element. There's a lot of words there to say simply that you must have a force that is less than the strength of a structural element. So historically, safety factors are used to describe the ratio of the strength of a structural element to the applied stress. Metals are predictable and the properties are easily established. Obviously, we use metals for 90% of railing. They exhibit a yielding behavior or permanent deformation before they fail. They're ductile in most cases, so they stretch out. So safety factors prescribed by code are usually in the range of 1.5 to 2, and that's usually for permanent set, yielding, or bending. Metal design is detailed in reference standards, and design is relatively straightforward. The reference standards are, for example, the Aluminum Design Manual or the AISC 318 Construction Manual. Glass, on the other hand, is a completely different story. Glass is a brittle material that fails suddenly. Because it's brittle, it does not, as you probably intuitively know, exhibit permanent deformation. Therefore, it's typically designed per an ASTM standard. That's E1300 for reference. It's based on probabilistic models depending on the load duration and a few other factors. As you can see in the slide, the building code addresses glass guards simply by stating the designer must use a factor of safety of 4. It's been a long debated piece of code language. It's been in there since about 1988, I believe. It will likely be changed in the near future a little bit to clarify that, but in the meantime, the current intent is to have designers divide the breaking load of glass. It's not easily defined. It's statistically highly variable, but you take a known breaking stress for the glass, divide it by 4, and compare that to the analytical stress. They're the stress that's in the actual piece of glass due to the wind load or the live load. This only applies to the glass in a guardrail system, not other non-glass components. The intent is also not to multiply design loads by 4 in a testing or an analysis. I only mention this because it's a pretty common misinterpretation. We will discuss in later slides some recent code developments as they pertain to glass guards, but the general direction worldwide is to provide a level of post-breakage safety. Measures have been taken to prevent glass from falling out of the supports and remaining in place with some degree of structural integrity after it breaks. This is achieved by requiring the use of laminated glass, and again, we'll talk about that later, and or tying the glass together with a top cap or handrail, or being able to demonstrate via testing that without top cap or handrail, the glass has post-breakage structural integrity. It's also important to distinguish between testing and engineered design. They do occasionally get confused with one another. Factors of safety are relevant only to the engineered design, not testing. In other words, for all metals and glass, testing involves applying a discrete load to the railing in the field. Usually for railings, the 50 PLF and 200-pound concentrated load. Loads are never multiplied by any safety factors. So testing, if required, should be discussed with the design team and written into specifications if necessary. Now we'll address our third S, which is style. And when we talk about member selection. Member sizing is, of course, driven by 3 major factors: loading, the material, and the geometry. Loading we previously discussed, and the connection to member sizing is fairly obvious. Larger imposed loads will result in larger members to resist them. Material selection is also straightforward. Stronger materials will require smaller sections. Most materials used in railing design are relatively close in their strength properties, so member sizes are not drastically changed by changing materials. This is when I'm talking about metals, and we'll talk about that in a second. The geometry of the railing is the most significant driver in determining member sizing. So note the typical efficient post spacing is around 4 feet. That's because at that spacing, you have a 50 pound per linear foot load times 4 is 200 pounds. That's equal to the concentrated load. There are a few cases where it might make more sense to stretch the spacing out a bit and reduce the total number of posts. That saves money on material and installation. But as you can see here, very large spacings might mean a much less efficient railing. You might need a very large post. Another factor that will affect your member sizing is the railing infill. In exterior applications, a solid or perforated panel system will collect wind load, which usually increases member sizing. In addition, using cables will induce additional stresses on end posts because the cables have to be tensioned. And finally, in exterior conditions, temperature loading that causes expansion and contraction of railing members should also be considered. Usually the temperature loading can be accommodated with simple expansion joints or slots in the base plates, but railing that is fixed or grouted into concrete requires a little bit more analysis to make sure that you don't have loads that accumulate because they are fixed into that concrete. This is especially true when you have aluminum, because all of these materials have different expansion rates. So steel and concrete have a very similar expansion and contraction rate, so they move well together even if the metal is fixed into the concrete, whereas aluminum expands about 3 times as much. So you can have problems either with the material or with concrete. Next topic is really about how safe a railing feels. In engineering, we typically refer to these sorts of issues as serviceability issues. Deflection describes how much a railing is displaced or moved under load. This is generally the shape that railing takes under load applied laterally at the top. The reason we mention this as being ambiguous is because the International Building Code does not specify a railing deflection limitation, except for the differential deflection between two pieces of glass specifically. To note, certain organizations such as LAWA, that's the Airport Authority in Los Angeles, and also DSA in California, the Division of State Architects, they do have deflection limitations, but they're very rare amongst jurisdictions. In addition, the feeling of a safe system is very subjective, especially a system which is in reality rarely loaded to its design limit. Now, differential deflection, if we back up to that topic, that's the deflection of one loaded panel of glass relative to an adjacent unloaded panel, is discussed in code, and that limitation is used to prevent creating a pinch point between panels. This requirement is a general building code requirement specifically for interior glazed areas, so it's implied, the implication is that it also applies to guardrails. It's probably more intended for storefront glass, but again, we use it for guards, both interior and exterior. The differential deflection criteria is met or simply non-applicable when you have a top cap or handrail connecting adjacent pieces of glass. One panel will not deflect relative to the other. They'll both deflect together. Deflection, although somewhat ambiguous, it's often neglected or overlooked. It's nonetheless important and should be considered. Design teams should think about the use of the guard, where it is in a building, and how it might feel to the groups using it. So a deflection limitation may be appropriate in lively venues or areas where crowds might gather and should be addressed in the specification process. Another area where it becomes an issue is high up. So if you have half-inch glass high up and you have a very small top cap on it, it might feel uncomfortable to users, even though it's not a safety issue. So contact a qualified professional, engage them, talk about this beforehand. If you have too strict a limit, just based on numbers alone, it could double or even triple material costs, especially if you're talking about glass. And in many cases, deflections can be mitigated by methods other than simply increasing the size of that glass, such as a stiffer top cap, for example. Let's talk about guardrail attachment options. The transition from the railing scope to the building. This table summarizes various methods of attachment, the applicability of which depends largely on the base or the building structure. For example, embeds may be the only option for very high loads or for locations where tension slabs are located, whereas core drilling may be possible on thicker slabs or curbs. Both the cost of material and labor and the aesthetic should be considered when choosing attachment methods. Anchors installed after the railing is on site, such as chemical anchors and mechanical anchors like screw or expansion anchors, allow for field tolerances, and require minimal labor effort. Many technologies have been developed in the last decade that allow for quick, strong, and clean anchoring in this manner, and it's usually the preferred method. Attachments become a key factor in both the efficient design and installation of any railing system. Uh, a chain is only as strong as its weakest link, if you will, and connection to the structure is not possible if you have inadequate structure. Railing geometry may be affected negatively. For example, post spacing has to decrease, or base plates may get very large if you don't have that substrate that's strong enough. Most concrete slab constructions or steel structures can easily accommodate typical interior railings. However, for many exterior railings that will accumulate wind loads, thorough consideration should be given to the attachment detail in the design phase. As with member sizing, design teams should consider loading, geometry, and material when considering anchorage options. Again, on an exterior application, very high wind loads, for example, you have a windscreen, it might be 6 feet tall rather than the traditional 3.5 feet tall for a guardrail. You get very, very large loads there. And again, it's suggested that you contact a competent professional early. You want to avoid potential problems later in the life cycle of a project. For example, changing a concrete slab or having to go through a concrete slab to steel below. Very difficult and expensive to coordinate. So now that we have covered the 3 S's, structure, safety, and style, as well as guardrail attachment options, let's briefly cover the most common code considerations driving your guardrail design. So 2018 IBC section 1014 and 1015 address standard height requirements for both handrail and guardrail. Chapter 10 is means of egress. For handrail, remember a uniform height can measure no less than 34 inches and no more than 38 inches. Guardrails should not be less than 42 inches tall per the code requirements. And when do you need a guard? When you have a fall over 30 inches. 30 inches or greater. For clarification purposes, the term guard and guardrail will be used interchangeably throughout this presentation. Let's talk about the term guard in Chapter 2 of the 2018 IBC, which defines the following. It's a building component or a system of building components located at or near the open sides of elevated walking surfaces that minimize the possibility of a fall from the walking surface to a lower level. And then, of course, we have handrail, which is a horizontal or sloping rail intended for grasping by the hand for guidance or support. Moving on to the term, let's go back to guardrail. Let's look more closely at that. The primary purpose of a guard is for fall protection. As we mentioned before, it's required when an individual could fall 30 inches or more within 36 inches of an edge. And it also must be constructed in a manner that would prevent a 4-inch sphere from passing through at any point, so people can't squeeze through portions of the railing. So 1015, again, means of egress, that discusses considerations such as where they required, the height requirements, the open limitations. And again, handrail, like a guardrail, you have the same exact loads on it, actually, the 50 PLF and the 200-pound concentrated load. 2018 IBC 1014, again, in means of egress, discusses considerations such as the height, graspability, handrail extensions, and intermediate handrails. Again, the most of what Chapter 10 does is describe how elements in a building have to be arranged so that people can safely move about and use that building. Let's talk again about some of the governing bodies that enforce code compliance. Talked about IBC a lot here. Everybody's familiar with that. You also have OSHA and ADA. Those are critical to ensure your railing is compliant. You have to check OSHA and ADA requirements. Also, in doing so, you should also check with your local building official. They might have more stringent requirements based on their jurisdictional in the jurisdiction. And sometimes they can't make a requirement that is less than ADA, OSHA, or IBC, but they can make one that's more stringent. And keep in mind that ICC is well aligned with OSHA and ADA. Either you have areas that are for OSHA, work areas that are not covered in ICC or ADA, and those areas have their own specific requirements. Where they do overlap, they have the same requirements. For the most part, I should say, the ones that I'm familiar with. There's one area of our industry, and we mentioned this before, that's recently gone through pretty sweeping changes over the past 10 years or so. That revolves around glass and spontaneous breakage. The new 2018 code has been updated to require the use of laminated glass because of spontaneous breakage in overhead conditions. So basically, they say you have to use laminate whenever there's a walking surface below, which is almost anything. So you can no longer use just simply monolithic tempered glass with no laminate. And the laminate, of course, is what's keeping two pieces of glass together in the case it breaks. It's pretty much adopted everywhere by now. There's probably a few states that are still in previous versions of IBC, but in any case, we usually recommend laminate anyway. It's really to prevent a situation where you would have a piece of glass gone from the series of glass that makes up a railing, and it's not apparent to the user. So this has happened in some cases on balconies of high-rise apartment buildings where you have a piece of monolithic glass break, it's not visible, and somebody falls off of the balcony. And it's pretty important to understand the new updated laminated glass code. So let's review this information in a little bit more depth. So again, 2018, we've increased the use of laminated glass for the reasons I already stated. And you also talk a little bit about quality. So one of the concerns with using laminated glass is the quality issue. Some people like to use monolithic glass simply for the look. Monolithic glass, again, contains no inner layer. As you see in the bottom right image here, you see that clear distinction between the two outer panes of glass and then the plastic laminating layer in the middle. So quality for laminated glass defines a mismatch as misalignment of the edges of two lights of glass when laminated. It might not be acceptable because it can be quite a bit. Usually what we do is limit that, and we work with suppliers to get that mismatch way down so it's really not noticeable. The upper illustration demonstrates the possible mismatch that can occur. It can be quite stark, and it can cause problems if you have holes in glass as well. Let's look a little bit at glass features. There's two different types of material that are typically utilized in guardrails. You have, again, the tempered versus the laminate. There are two common inner layers, the PVB and SGP. We've talked a lot about laminating. What is that? It's a polymer material that goes in between the glass that is heated up with the glass and put under pressure, basically adhered together. PVB is the most common. It's most cost effective and it's best suited for interior uses. It's much easier to use for manufacturing. It's pliable. The second more expensive option is SGP. That has more like a rigid plastic feel. It's much stronger. It's recommended for exterior applications. And it also has been more difficult to get in the past few years here. But it does provide a much higher strength and stiffness than does PVB. So how do we get the glass to be as strong as we need it for a guardrail? Well, we temper it. It's approximately 4 times stronger than ordinary or anneal glass. There's also something in the middle called heat strengthened glass. So you can go anywhere from fully tempered down to annealed or just ordinary glass. During the tempering process, the glass passes through a tempering oven. It's heated to a temperature of more than 600 degrees Celsius. The glass then undergoes quenching, high pressure cooling procedure. You've probably heard of that in the context of metals. As a result of the quenching, the center remains in tension while the outer edges go into compression, which gives tempered glass its strength. So like other brittle materials, glass is weak in tension. What we do is add this compression, basically a pre-compression. So you have to overcome that compression in the glass before you start to put tension in the glass, and that makes it stronger. When broken, the tension force and the will force the glass to crumble into small granular chunks versus splintering into jagged shards as annealed glass does. So it's another important consideration. If you have a piece of annealed glass, you break it, it ends up being in very large jagged chunks. Whereas tempered glass, you've probably seen this broken before. Your windshield on your car is a good example. It breaks into a tiny, millions of tiny little segments. And that's why in overhead conditions, they require it because they'd rather have this rain down on you than giant shards of glass. So there's not only different types of glass and different types of inner layers, there's also different types of edge treatments. This is more on the aesthetic side. It does affect the stress level a little bit. Ultimately, flat polished edges are the industry standard. That also gets you slightly better behavior in the glass because you get rid of some cracks, micro cracks, and discontinuities on the edges. Pictured examples of edge treatments are not common due to the increase in pricing. The miter, bevel, flat, those different treatments are not really common. They do cost a lot. But in general, you're either polishing or not polishing an edge. Not polishing an edge is usually one that's not visible, but you almost always polish them if they are visible. So in terms of decorative guardrails, glass guardrails generally fall into one of these three categories. You have base shoe supported, post supported, and point supported. You want to think about those, the items listed here too: performance, budget, and aesthetics, of course. So some of the advantages when designing with base shoe supported guardrails are versatility, ease of attachment, and fabrication. These systems also allow you to customize your top rail and your hand railing. Just go to the slide here before I mention that. So base shoe supported glass is simply glass that's sitting in an aluminum channel. Here you see in the middle is our proprietary dry glaze system. There's other dry glaze systems such as taper lock. CRL sells a taper lock. You might have heard of that. Dry glaze is just not using a cement or gypsum or plastic or polymer epoxy type grout in that shoe. So there's a lot of advantages. Again, you can customize pretty much anything here. You can customize the glass. So you can see here that you have a frit on the glass that makes some text. You can put a pattern on the glass. You can customize the top rail. That can be a rounded profile or just a rectangular or very slim profile. And you can, of course, add handrail to it if you'd like. And here's some other items that you can pretty much make it fit in any area by fabricating the shoe in any length or having it cut in the field. So the next consideration, or the next type of railing that we're going to talk about, is post-supported system. That's pretty straightforward. It also involves many different types of railings. And generally speaking, how do we define it? It's just a post in between those pieces of glass with glass infill between the posts. So usually the structure is made up of steel or aluminum, and the infill is just the glass. Some advantages working with the post supports are enhanced design aesthetics, opportunity for customized systems. It really adds a nice design element to any sort of building. It can match the aesthetic by simply designing that guardrail to be what you want it to be. So you want to think about this. If you're doing a post-supported system, think about that early in the design process. We see a lot of these come up as an afterthought. Oh, we need railing here. And you're left with little or no structure to attach the railing to. And if you have a certain post, you want to match the aesthetic of your building, you may be limited in your options if you haven't thought about it early on. Remember earlier in our presentation the importance of structure we discussed as part of the 3 S's. And attachment is one of those. Perfect example of why upfront coordination with the railing manufacturer is important to an efficient design process. And again, the other thing is the expectation addressing the finish, tolerance. We talked about all these things a little bit, and functionality of the system should be addressed within the specifications. And the reason I mention that is because oftentimes the finish becomes a highly contested topic because it can cost a lot of money. If, for example, you have in this image a stainless railing, you want no welds to be visible. You have them ground down to a NOMA number 1. That's just basically so you can't see it. And it can cost more than the welding and the material just to do that finishing. So you want to think about that very early on as well. It can't be an afterthought. Okay, let's talk about point-supported guards. What are we talking about there? We're just talking about discrete places on the glass where the stress is concentrated and taken back to the structure. So what are the advantages? The point-supported system, it's a modern alternative to standard base shoe design. So you can see here you could have a base shoe, but that would be on top or on the edge of the slab. It's a little bit more obtrusive, whereas these points you can leave made visible, and they can become part of the aesthetic as well. Provides a nice transition from the curtain wall to a guardrail system. It's used in that application a lot. And you can, of course, put a frit or silkscreen pattern on the glass. Now, this usually does require thicker glass because you concentrate that load at various little points, and your glass stress can become quite high. And oftentimes, you can see here the points are on the edge of a slab, meaning that the glass is effectively getting a little bit taller. So you do increase the glass cost somewhat. Um, you can also have deflection issues if those supports are too far down. The glass again is effectively taller. Caps or handrails should be used to limit deflection, although you can also increase the glass. That usually has a higher cost implication. One thing that you have to keep in mind for installation is that you need holes in the glass. That limits tolerance. We have a fitting that does a really good job of taking up that tolerance, but you need more experienced installers usually to install this glass. Now, it's really important to consider labor when making decisions on which system you use. You can see a little chart here. It gives you a little bit of information about different systems and the cost. But labor can account for 30 to 40% of a system's overall cost. For example, the amount of labor for a base use system can be 2 times that of a post or point supported system, which should be taken into account when budgets are established. But as we said, you also need a pretty good team to do the point installation, so there's some trade-offs there that you have to consider. In any case, labor, because it's 30 to 40% of the design or percent of the total cost, you definitely want to consider that. Now let's talk about metal railings. So these are probably the majority of typical railings in buildings in general. We use a lot of glass, of course, in commercial, in sports settings and things like that. But if you think about overall amount of railing in the commercial, industrial, everywhere, really, most of it is metal. So specifically, though, we're going to talk about decorative metal. So that's stuff that's not just off the shelf or industrial use. There's 3 things to keep in mind: performance, budget, and aesthetics, as usual. Let's examine the features of metal when choosing aluminum. So why would we choose aluminum? Well, for one thing, it's non-corrosive. So it won't rust like steel will over time. You might get some corrosion on it if it's not anodized or painted, but that's not going to be visible. It's just going to be a white powdery substance. It's not a big deal. It has a much better performance, ability to outperform steel in an exterior environment, unless the steel is either galvanized or coated. It generally has the same tensile strength as steel because it's usually heat treated. It has a little bit higher deflection though because it's actually 3 times less stiff than steel. But that can be addressed by utilizing the appropriate member sizes. Member sizes and spacing can be customized, of course, to make that mitigate that issue. It's extruded and you can use custom dies, so you can fabricate it almost any way you want to. So in general, aluminum is our preferred material. Again, partially because we use it in a lot of exterior environments. It doesn't corrode. It's much lighter, much easier to install, and you don't have problems with finishes that you might have with hot dip galvanizing steel, burrs, things like that, or painting it, chipping it, having to refinish it in the field. So we talked a little bit about finishes. Anodizing is the most standard finish for aluminum, and you can do that in a lot of different colors. That doesn't like chip off. It's a surface treatment. It's a chemical procedure. Aluminum can also be painted with liquid or powder applications. The nice thing about that is we talked about that with steel. You chip it, you damage it. Yes, we still have that same problem with aluminum. However, you don't get a rust bleed out if you have a chip that happens in the life cycle of the railing. So let's talk about steel now. It's a popular choice, of course, for guardrails. Why? It's cheaper than aluminum. It's easy to fabricate. Many people do it. That's pretty much the reason why it is out there in probably 75% of applications. The only problem, of course, is that you need to hot dip galvanize it or paint it. You need to keep it, maintain that coating. The galvanizing is a chemical procedure. That's actually not just a coating, though. It's a chemically bonded zinc layer. So that can be effective if you don't mind the hot dip galvanized sort of industrial look. Of course, you can paint it. There's good coatings out there, but you have to maintain those coatings. And as we talked about, Here's the two most common. To go into some detail on those again, the hot dip galvanizing doesn't really need to be maintained per se. The powder coating or liquid paint needs to be maintained over time. You need to keep coming back and putting that coat on. Probably with good coatings now, probably after 10 years or so, maybe 20, you'll have to do something else for long-term sustainability of that finish. Stainless steel, that's also commonly used in architectural railings. It's more expensive, of course. It's more expensive than aluminum. It's just as heavy as steel. You have to keep it pretty clean. It's not going to rust per se, but you can get it contaminated. So you have to also treat it and use the right materials when you're welding and things like that to make sure that you don't have problems later on down the line. There's a lot of different finishes. It's a good material. It's generally the most widely used in architectural applications, no doubt, because of the appearance. People like that stainless look. Don't have to paint it. You shouldn't paint it, in fact, because the stainless is a nice finish all by itself. The one thing to note about the way that it has to be treated is it's a process called passivation. That's just a note that you should keep in your head. Doesn't mean you need to know a lot about it, but it really provides long-term corrosion resistance when that material is passivated. So let's talk about finishing in a little bit more detail for stainless steel. It's a key part because, as we talked about, if you have welds that need to be NOMA number 1, it's going to cost you a lot of money. But you have two different types of weld that are typical weld finishes. You have a NOMA number 4 and a NOMA number 1. NOMA number 4 is just as welded. NOMA number 1 is polished. And when I talk about polishing here, here's a couple of the most commonly used. Number 4 brush is very common. You can go up to a mirror finish if you want with stainless. Not really recommended because it's going to be very, very costly. There's a little bit more information on passivation there. Again, I would just keep that note in your head that you need to passivate stainless steel to make it corrosion resistant over time. And it's a good idea to specify that. Here's some more information on welding and that NOMA stuff that I've been discussing. What costs the most? Of course, finish number 1 is much more costly than finish number 4. Although if you have good welders, I would never recommend going to a finish number 1. That's something that people generally don't notice. If you have good welds that don't have weld splatter and that are coined nicely, that's where you see that back and forth positioning of each weld. Coining, we call it in the industry. If you have that very nice coining, you really don't need to finish it to a number 1. Like I said, it can cost you twice the amount of money for labor if you decide to use a NOMA number 1. So let's talk about infill options. What is infill? Infill is the material between the top of the railing, the top bar or the handrail, and the bottom of the substrate of the building. There's 3 main types that we use. We use mesh, pickets, and then we use glass, as we talked about before, and also cable. So really the metal options are cable, mesh, and picket. Pickets are more of a utility style. Everybody's familiar with what that is. Vertical up and down pickets. Cable and mesh are more decorative, usually a little bit more costly, but it just depends on what you use there for the mesh. So here's the 3 examples: mesh, cable, picket. Let's examine each of the 3 infills a little bit with their advantages and considerations to keep in mind with each type. So mesh is a great choice since it's customizable, but it can also be expensive because it might be a custom. There's some off-the-shelf stuff that is perforated, or certain meshes that you can get, woven wire, things like that. Just depends on what you're getting. Cable is cost-effective and clean. That's of course what makes it so attractive. The only issue is that you do have to be a little bit more cognizant of the length of the rail sections because the cables need to be tensioned, and the end post can get sort of obtrusive depending on the climate you're in. Colder temperatures, if you're in, for example, Minneapolis or Chicago, you have larger temperature swings to consider. The end posts usually get a little bit bigger because of that. There's some engineering challenges that you have to overcome. Okay, and then let's talk about glass just a little bit. Um, as we have already, this is the other material. Um, this is the other material that's used for infill. And now I just want to start this discussion by talking about really how these materials contribute to sustainability. This has been a huge thing in the industry in the last 25 years, really, that we're talking about LEED certifications and things like that, and generally being more cognizant of the environmental impacts of material. So there's a lot of technologies for recycling of glass. We know that we've been recycling glass for probably 50 years, but we can actually now remove the inner layer from laminated glass. So approximately 90% becomes glass cult that can be recycled in a number of new products, while the inner layer scrap is reprocessed into pellets and recycled into new products. So that plastic is taken and recycled. So glass has even gotten more green. And really, it's one of the most, in terms of what's used in the building, it's one of the most really just basic materials. It's made from sand, soda ash, and limestone. It's been used for a long, long time. That combination of three basic, really abundant raw materials. So it's essentially a infinitely recyclable material in a sense. Then you have aluminum. Aluminum, of course, is very recyclable. 75% of all aluminum ever produced is still in use today. So that's pretty astounding. In addition to being 100% recyclable, it retains its properties indefinitely, which is great. That's not like plastics and polymers. Plastics and polymers are usually good for one recycle. They usually end up in a different material altogether, something that doesn't have to be um, you don't have to meet stringent mechanical requirements because you lose a lot of those when you recycle it for a lot of polymers. So aluminum is great. It really, based on the amount of greenhouse gas you can see in the second paragraph, it really does a great job relative to other materials used. And then you have steel. 90% recycled steel. Most structural steel contains 90% recycled steel scrap. And in addition, at the end of a building's life, 98% of all the structural steel is recycled back into new steel products. So almost the same there. And if you read that second paragraph, the Steel Recycling Institute states that the North American steel industry voluntarily invested in research and development, producing technology that has reduced the CO2 intensity per ton of steel produced by 37% and energy intensity by 32% since 1990. So that's always been the knock against steel, of course, is that it's very energy intensive to make initially. So is aluminum, so is concrete. So those are all things that make recycling pretty important. So that's all we have. This concludes our presentation on efficient design utilizing decorative guardrails. There is specific LEED information as well as case studies in our appendix of this presentation. I encourage you to review them for great examples of efficient design of railing systems on completed projects. I hope the information shared in this presentation will help you to specify and design guardrailing systems that are safe and beautiful on your upcoming projects. Thank you for your participation. And we hope you enjoyed all of it. I will go into the slides here in the appendix and scroll through them slowly so you can see some of the other material and resource credits as well as some of the examples.